Thank you. So I'm going to be talking about operational algorithmic game semantics, which is joint work with my supervisor, Andrzej Murawski, and is work we presented at LIX last year. So what we study is a variant of call by push value with first order state, for which we're going to build a fully abstract model using operational game semantics. We're then going to refine that model for certain types into an automaton, from which we obtain an algorithm for determining contextual equivalence. And then through this, we obtain a decidability result, which subsumes all results obtained using finite alphabet automata for finite tree idealized algol and RML. So call by push value is a calculus into which call by name and call by value evaluation orders can be encoded. It stratifies types between values and computations, following the maxim that a value is, a computation does. The key feature is then funcs, which freeze a computation into a value, and force, which unfreezes them. We have a return, which embeds values into computations, and an operation similar to monadic bind. Thank you. So we include in our language good integer references, but also a bad variable constructor in the style of Reynolds, and that's so that we can match earlier work using idealized algol and RML. So as we've seen quite a lot already today, we define contextual equivalence and indeed contextual preorder by testing with contexts. In this case, those contexts which yield computations returning a value. So interestingly, as you probably all can guess, in general, contextual equivalence is not decidable. And this is slightly surprising, given that we are dealing only with finite tree types. The reason for that is that in our setting, the presence of higher order types allow the context to obtain some factory thunks that can essentially force the generation of arbitrary many new locations. So as an example of contextual equivalence in this setting, we can see that forcing some thunk f and passing it a thunk which just returns the constant 1 is the same as creating some reference, setting it to 1, and then passing a thunk which reads that reference to f. So to decide contextual equivalence, we're going to appeal to game semantics. And I'm going to briefly mention a couple of points of background to put our work into context. So as usual, in game semantics, we model a term as a strategy for a question and answer game. And for us, we're going to call the term the player, or P, and the context the opponent, or O. The key result that we're interested in is one of full abstraction. That is that equality in the model coincides exactly with contextual equivalence. And these results are one of the key features of game semantic models. And one thing I'd like to just highlight is that a lot of models are focused on composition and compositional approaches and employing categorical presentations. And the models we use are not so compositional. So game semantics has previously been applied to deciding contextual equivalence in a line of work referred to as algorithmic game semantics. Here, the idea is to construct automata, to encode strategies, and then appeal to language equivalents of automata to decide contextual equivalence. The results have been shown for both call by value and call by name languages. One of the important properties of these automata is that they're built up inductively by following those compositional models, and that necessitates certain constructions like linking the final states of some automata to the initial states of others. It also constrains the constructions in some way, so that we can only use so-called canonical forms, which are essentially obtained by eliminating certain beta redexes. So instead, we're going to build upon operational game semantics, which we've seen quite a lot already today. So in this presentation, we have a concrete representation of strategies as traces of some label transition system. And we claim that those label transition systems form a very good starting point for which to obtain an automaton, due to the inherent similarities. Namely, they both have a notion of state, they both have a notion of transition. So just to highlight some aspects of our traces, they're built over some infinite set of names, which are used to encode thunks that have been passed across the boundary between the term and its context. We have alternating actions of question and answer, of player and opponent actions, which can be either question or answers. So in a question action, like these ones here, we have some which correspond to forcing some thunk and consist of a name applied to some sequence of arguments, and those arguments have a name in place of thunks, which makes them abstract in a similar sense to as was discussed in previous talks. The point of the names is that they encode the origin of the thunk. So, for example, W here means that we're referring to the second argument of F. And these are called head names when they're used in an action. So something to take away from this is that these names are similar to the notion of pointers in a classical game semantic presentation. For technical reasons, we have continuation names used to answer a question, and this corresponds to returning a value. We will have some well-formedness conditions, namely bracketing, which is the standard notion that we must answer the most recently unanswered question, and visibly, which corresponds to only using things that are lexically in scope. So in this case, visibly would mean after the answer of C1, we would be unable to use W. So this is our transition system that generates this. We have we have a state with an explicit stack component separate. We have active states where P is to play, and they contain some term being reduced. Into this, we can embed the operational semantics in the kind of standard manner. When we encounter returning, we, as said, generate a player answer, and encountering a name or trying to force some name generates a player question. Here is kind of the first point at which our model deviates from those for call by value, which is that instead of passing a single name, a single value, we instead consume a sequence of values. And that corresponds to the fact that call by push value validates the currying law, which means that, in effect, a sequence being passed is the same as a product. So once we have player actions, we end up in passive states where the opponent is to play. A key feature here is then that we have gamma, which is some component that gathers up a mapping from names to thunks, so that when we have a opponent play, we can then work out what the appropriate behavior of the player is. Importantly, gamma is something that's going to grow over the execution. And we use the stack for storing evaluation contexts because of the bracketing discipline. So we've obtained a full abstraction result, which is essentially that trace equality means contextual equivalence. As an example of this, how these traces distinguish, consider the following program, which forces some thunk name F twice to obtain two new thunks, and then differ in, so we have M1 which forces G1 and M2 which forces G2. And we can distinguish these two by these traces, where in one case we use G1 and in the other we use G2. So if we want to turn our label transition system into an automaton, the first problem we encounter is that we have infinite traces. So this is due to the use of names. Now, to solve this, we make it so that the name introduced, or names introduced, are determined solely by the head name used. And we do this using something called a name scheme, which associates a thunk name to each thunk type appearing in the typing environment. So here we can kind of see it with colors. H is the kind of outermost thunk, but then where we have these argument thunks, they are referred to as I and then J and K, respectively. We also have a fixed continuation name associated with each thunk name, which refers to where we are to return the value of forcing that thunk to. If we link together the names with the thunk names of the arguments that they take with solid arrows and the continuation names with dashed arrows, we get something that is an analog of the notion of an enabling relation in an arena. And in this sense, we can see name schemes as a reformulation of arenas that in some way captures the shape without the concrete moves that would correspond to base types. The result of applying this process of renaming basically to a trace is that we get a canonical finite presentation of traces. There's a problem with this, though, which is that it's not faithful. In doing so, we have equated the traces that previously distinguished M1 and M2. We fix this through a process of marking, essentially translating a single trace into a set of traces where we mark all occurrences of a single O name in the original trace. So to distinguish M1 and M2, we can see that in this trace here, when the first occurrence of G is, the first introduction of G is marked, the G used in the question is marked, whereas in the traces of M2, when the first introduction of G is marked, G is not marked, and so that distinguishes the two. This is actually similar in spirit to something called the one-pointer presentation that was used in work on O-strict RML. So the point of this is that we then recover our full abstraction for a particular fragment that we're going to define. So we still actually face an issue with generating these traces. So this, one way this arises is if we consider the following two terms where we have two thunks with different behaviors that are given the same name by the name scheme. So in this case, the one returning 1 and the one returning 2. We will somehow need to distinguish between the two names, the two occurrences of the name inside the LTS when we're storing these thunks into gamma. To achieve this, we're going to index occurrences of names. Naively, indexing would lead us back to having an infinite set and end up with an infinite state space. So instead, we adopt something called, which we've termed recycling schemes to allow us to reuse those indices. The first scheme is based on the fact that a player answer which introduces no names makes all names that were introduced since the opponent question it is answering become unusable, and this is actually a fairly simple consequence of the visibility constraints. We can then implement this in a label transition system by having some component eta that's going to map names to the next available indices, and mu, which we're going to use to store a kind of history of eta. And then when we have a player answer, we can reset eta using that mu component, and we can prune everything else back to those things that are the indexes that are still going to be visible and ignore all of those that aren't, which gives us back a finite state space. We actually need a second recycling scheme, which I won't say too much about, but essentially gives a situation in which we will have a temporarily names that are temporarily unusable. And in that case, what we can do is use the fact we've got this stack and store those names and the information related to them onto the stack, and then in a answer action, we can pop them back off and restore that information. So putting it all together, we end up with a slightly more complicated label transition system. Essentially, we add in some duplicate rules as well, some extra rules to handle these recycling schemes. But in essence, it still has a similar flavor to the original one. So we actually can establish a result for something we've called the PTR fragment, which is that the refined LTS I just presented indeed produces the renaming of traces of the original LTS for some given name scheme. And a consequence of this is that we retain full abstraction. In fact, we can show that that refined LTS is then a visibly pushdown automaton. So that's a pushdown automaton where we partition the alphabet by the stack action that can be performed, so a push action, a pop action, or a no-op action. And because of this, we get that visibly pushdown automata have a decidable language inclusion problem, and so our contextual equivalence is decidable. We actually need to define the fragment that our translation works for. So to do this, we can polarize occurrences of U between those that produce O questions and those that produce P ones. So we can then look at these two types, where the first type is one that breaks the first recycling scheme because, in essence, it allows a player answer to return a thunk. And we will observe that there are nested occurrences of U+. We can find a similar example for that breaks the second recycling scheme, and again, it has this property of nested occurrences of U+. So we can actually, when you work out the detail, it turns out that you can define the fragment to be that which doesn't allow nested occurrences of U+, but allows unrestricted use of U-, and that's what this grammar captures. So finally, we can actually give translations from the prototypical call-by-name language, idealized algol, and call-by-value language, RML, into our variant of call-by-push-value, and we can prove them correct using our fully abstract model. This proof exploits the definability result of our model, which is that for any given trace, there is a context which induces the even-nth prefixes of that trace. And in general, these contexts are going to be call-by-push-value contexts. But when we're interested in traces arising from the translation of RML or IA terms, we can actually show that the contexts will be equivalent to the translations of contexts in the appropriate language. And doing so, we are able to therefore say that our work matches that of third-order idealized algol, work on third-order idealized algol with iteration, and for something called the O-strict fragment of RML. We can actually find a smaller fragment where our construction gives rise to a deterministic finite automaton, and that occurs where we don't need to use, where the stack is bounded, so that we can make it part of the state space, and that actually arises when we don't need to use our second recycling scheme. And that gives rise to this typing judgment, this set of types, which we can see includes second-order idealized algol and something called the bi-strict fragment of RML. So, in conclusion, we have presented a new approach to decidability results that we call operational algorithmic game semantics. We believe it's advantageous as OGS models are easier to construct and can be reasoned about using operational intuitions. The resulting automata retain an operational character, which could be useful for other verification tasks. And we believe that the approach should extend to other frameworks. We've also done some exploration on using more powerful automata, in particular data automata, where the notion of name is more natively representable as data values and avoids the need for type restrictions, as we had here. So, yeah, thank you. That's
Thanks. We have time for one or two.
I was wondering about the complexity result you've managed to get on canonical forms. What are the shape of those canonical forms? I mean, is there like a nice description since you're in call-by-push-value that you could use, a kind of polarization? Or?
The canonical forms that we defined were, in some sense, more similar to the call-by-value canonical forms. They're not especially nice in any particular way. There's a inductive definition of kind of how to translate things into canonical forms that shows they always exist. But no, there isn't anything particularly useful. I guess in essence, it's the, kind of any application is always with a variable that in some way you know will arise from the opponent, rather than being something that will be substituted with something from inside the player, or inside the term itself, but yeah, nothing particularly elegant about them.
Thanks.
Thanks for the talk. So, yes.
Do you have the
And code by name,
Mhm.
I think there is a type classification of the
Mhm.
non-decidable type. So this opens up new types, I think.
Yes, so we don't have in effect, we don't have the undecidability result to bound the top. In some sense, you obtain some of the results by the embedding that you have from these languages. So you can say that there are certain types that will be undecidable because, well, anything that you would encode fourth order idealized algo is going to end up being undecidable. Following the work that's been done on RML, there's, I believe, one case that's unknown whether or not it's decidable because it reduces to a no-open problem. Presumably, you would have that similar case would arise in call by push value. But yeah, we've not kind of looked at the undecidability result yet.
Okay, thanks again.